All right, so today we're going to be talking about power and torque relationships in synchronous machines. All right, so we're going to draw two simple diagrams here because we know that synchronous machines can very regularly be used as both a motor and as a generator, right? So for motors, we're going to have something like this for our power flow diagram, right? So over here on the left-hand side, we'll have our electrical input power. We'll hit you guys with some math for this in just a moment. Here in the middle is my developed power. And so that's effectively what's going on with my conversion of electrical power into mechanical power. And then lastly, over here on the right, we're going to have our output mechanical power. So we've got something going on like this in general, but then we also have to take into account our losses, right? So we're going to have electrical losses that are taking away some of our input electrical power. And these electrical losses are going to be things like our stator copper losses, we might also have our core losses. And typically speaking, we might have some rotor copper loss as well. But remember that in a synchronous machine, our rotor is excited with a DC current, typically small. And so those losses are usually small enough so as to be neglected. So unlike an induction machine, we're not really going to bother with the rotor copper losses too much. So what that means is that the power that's delivered across our air gap and our developed mechanical power are pretty much the same quantity for a synchronous machine. So like, I'm going to put up here, so PR is approximately equal I'm going to call it actually PD for our developed power. So our rotor power and our developed power are roughly the same thing. If we completely neglect the rotor copper losses, they are literally the exact same quantity. Now moving from the developed power to our output mechanical power, so the power that's delivered to the shaft, we're also going to have some losses there. So these will be our mechanical losses. And this is going to be like our friction and windage loss. As well as any stray losses that we might have. They just get lumped in, okay? So this is pretty darn similar to what we saw with an induction motor. The only real difference here is that we're not going to worry about our rotor copper losses. For generator operation, it's going to be literally the exact same graph, except that the arrows are going to go in the opposite direction. So our input power is going to be mechanical, our output power is going to be electrical, but all of our losses are going to occur in the same place, right? So for generators, we would have something like this. We have our input mechanical power. Here in the middle, we have our developed power. So that's the power that crosses the air gap, effectively converting our, in this case, mechanical energy into electrical energy. And then over here on the output side, we have our output electrical power. We are going to lose some of our input mechanical power to mechanical losses. And we are going to lose some of our developed power to electrical losses. So we now have a good understanding of what the power flow looks like. So now let's introduce some equations. So I'm going to put things in terms of either electrical power, developed power, or mechanical power, and we can choose whether, if we're using a motor, we know that the electrical power is the input. If we're using the device as a generator, we know the mechanical power is the input. Okay, so I'm just putting things as generally as possible so that we really just have one set of equations, and we just need to know whether we're using the device as a motor or a generator in order to apply things correctly, okay? So let's start with our shaft power, okay? So our shaft power is simply going to be the product of the torque at the shaft multiplied by the speed of rotation. So that's our mechanical power one way or the other. So for instance, if we're told that we are using a device as a motor, and let's say that it's a 5 horsepower motor, that would be our output shaft power. And from that, we could determine our torque if we knew what our speed of rotation would be, right? So this one simple, small relationship kind of summarizes all of the mechanical power in the system, whether it's on the input side or the output side. For our electrical power, this is going to look like three times the magnitude of our phase voltage times the magnitude of our phase current cosine the angle theta, where, just to be super clear here, this bit is nothing more than the power factor at which our electrical side is operating. So this can also be expressed as 3 times the magnitude of our phase voltage times the magnitude of our induced voltage divided by our reactance, our synchronous reactance XS multiplied by sine of delta, where delta is the angle between our induced voltage and our terminal voltage, like before, okay? So technically we've made an assumption here, but it's an assumption that is overwhelmingly correct. So I'm going to put 4 XS much greater than RA. So this second representation is an approximation. The first representation there using cosine of theta is a more exact representation, but realistically for the overwhelming majority of synchronous machines, you're going to wind up getting the exact same result, okay? So we have our shaft power, we have our electrical power. So now let's talk about the developed power that's going on for the energy conversion, okay? So our developed power, PD, can be expressed as PD, our developed torque, times omega m. And this is going to be the same thing as 3 times the magnitude of EA times the magnitude of IA cosine the angle theta plus the angle delta. So just to recap things here, theta is the angle between VA and IA, and delta is the angle between EA and VA. From this relationship, we can see that our developed torque, PD, is just our developed power divided by omega m. And that's going to come out to be 3 EA V phi A over, actually, let me do it this way first. EA IA cosine theta plus delta. We're going to divide by omega m, which for a synchronous machine, omega m and omega s are literally the exact same thing, because our whole point of a synchronous machine is that our rotor is spinning at the exact same angular frequency as our excitation is. And then using the relationship of how IA is related to V phi A, this looks like 3 EA V phi A divided by omega s times x sub s times the sine of delta. And once again, we're making the assumption here that xs is much greater than Ra. So these are effectively all of our power and torque relationships for a synchronous machine. It does not matter whether we're using it as a generator or as a motor. Everything has been taken care of. So let's work some problems. So let's say that I have a three-phase 100 horsepower ,60 hertz, 480 delta, 277Y volts RMS rated, 4-pole synchronous motor has an armature resistance of Ra is equal to 0.15 ohms and a synchronous reactance of XS is equal to 2 ohms. And each of those are per phase quantities. At the rated load, and a power factor of 0.8 leading, and this is actually something interesting here. I might want to talk about this in a moment. The motor efficiency is ,95%. And then I want us to determine the maximum developed torque. So the interesting thing, or at least it's interesting to me, hopefully it'll be interesting to you guys, thing about a synchronous machine is that unlike an induction machine, it can actually be operated at a leading power factor, a lagging power factor, or unity power factor, right? So the inclusion of synchronous machines in an industrial setting actually provide or can be established such that they provide some sort of active power factor correction whenever those machines are running. So in some specific instances, industrial sites will actually run an unloaded synchronous machine as a power factor correction device instead of utilizing a capacitor bank, like what's been discussed in your previous power classes on grid scale solutions, right? So you can use a combination of synchronous machines and induction machines in order to not have to employ standard power factor correction techniques. And it's all because the synchronous machines can actually be operated at a leading power factor, unlike an induction machine. So that's something that's pretty darn interesting, at least to me. All right, so if I wanted to find the maximum developed torque, what do you guys think I would need to do? So if we scroll up to our equations here, when is my developed torque TD going to be at its maximum? Or what's the maximum possible numerical value it could have? If the cosine bit right there weren't there, that's just the amplitude of a sinusoidal signal, right? Or the sine bit over here weren't there. So if we were saying that sine of delta was equal to 1, the maximum value would just be this thing over here. So really just the amplitude portion is our equation for maximum torque. We don't have to necessarily worry about our angles, theta and delta, okay? So our developed maximum torque, TD max, is given by either, that's this, 3 times EA IA over omega S, or 3 EA V phi A over omega S X sub S. Either of those relationships give us our maximum developed torque. Okay. So what pieces of information that we need to throw into this equation do we already have? Anybody have any thoughts on that? So in my opinion, there's at least one super obvious one. XS, yeah. So we know, I'm going to do this in a different color, that XS is equal to 2 ohms. So we definitely have at least that part of that second relationship. I think we have another part of that second relationship as well, though, okay? So that V phi A is the Y-connected voltage that's appearing at the terminals of our motor. And since we were given the rated voltage and we're told the device is effectively working at rated quantities, I think we can say pretty safely that the magnitude of V phi A is 277 volts RMS. So now we need to figure out what EA is and what omega S is. And if we have those two pieces of information, we're able to determine our maximum developed torque. So let's figure out the easier of the two quantities first, omega S, okay? So omega S is just our synchronous speed measured in RPMs, which we actually don't know just yet, times a factor of 2 pi over 60, We use that when we were dealing with induction machines. It's the exact same relationship to go from RPMs to radians per second. Well, NS is just 120 F, our linear frequency, divided by P, our number of poles. And then that gets multiplied by that 2 pi over 60 term. And so this simplifies to 4 pi times our linear frequency divided by the number of poles is our angular speed of our motor, right? So that's going to look like 4 pi times 60 hertz divided by 4 poles comes out to be 188.495 radians per second, equivalent to, I think this would be 1800 RPM. All right, so omega S is taken care of. Just using the exact same relationships that we were using for induction motors, right? Calculating our synchronous speed is the same for regardless of the type of motor that we have. So now the only thing that we're missing is the magnitude of our induced voltage, EA. In order for us to figure that out, we're going to have to look at the equivalent circuit of our motor, right? Particularly, we're going to have to look at the stator side of things. So the equivalent circuit for one phase of the stator looks something like this, where here's our voltage EA, here's our resistance RA, here's our synchronous reactance JXS, and then here is our terminals, right? We are applying a voltage V phi A here, and because we're using this device as a motor, we should expect our current to flow from our terminals towards our induced voltage like I've drawn. From this relationship, or from this equivalent circuit, we can see that EA is going to be V phi A minus IA times RA plus JXS. Well, RA was given to us in the problem statement. V phi A was given to us in the problem statement. XS was given to us in the problem statement, but we don't know what IA is. So how might we go about finding quantity IA? Well, let's scroll back up here and let's look at some of our relationships, right? So up here where I defined our electric power, I said that the magnitude of IA was equal, or excuse me, the electric power was 3 times the magnitude of our phase voltage times the magnitude of our current IA times the cosine of theta, where cosine of theta was just our power factor, right? We have some specific power factor that we're dealing with here, so we should be able to figure things out. So if I take that relationship that my electric power is 3 times the magnitude of V phi A times the magnitude of IA times our power factor, and rearrange it, I'll find that the magnitude of IA is given by our electric power divided by 3 times the magnitude of our voltage times our power factor. So we have an equation here to figure out the magnitude of IA. We'll worry about the phase angle in a moment, but we've now run into a slightly different issue in as much as we don't know what our electric power is. However, we were told that the device is operating at rated output mechanical power, and we were also told what our efficiency is. And from those two pieces of information, we should be able to figure out what the electric power is, right? So this could be written as, I'm going to put the 3 times V phi A divided by power factor, or excuse me, multiplied by power factor down here. So knowing mechanical power and efficiency, how do I get electrical power? Right. So since this is a motor, our efficiency N is always defined to be our input power divided by our output power, which is going to be our electrical power divided by our mechanical power, right? So it looks to me like our electric power is just our efficiency times our mechanical power. You're 100% right, Ron. I'm just losing my damn mind. Should be P out over P in. Thank you for that. And so that would be mechanical up here, electrical down here. So doing it correctly, and thank you very much for the correction, Ron. Our electric power should look like P mech divided by our efficiency. Thank you for that. So I'm going to put P mech up here and eta down here. I'm going to put numbers in this thing just so that we can see how things shake out, and also to remind you guys of the conversion factor that we're going to need. So our mechanical power is 100 horsepower. And then there are 746 watts per horsepower. Down here, we're going to have 3. The magnitude of our voltage was 277 volts RMS. Our power factor was 0.95. That's not right. Our power factor was 0.8. Yes. And our efficiency was 0.95. And so this should give us a current of 118.120 amps RMS. So we know the magnitude of our current. How do you guys think we're going to get the phase angle of our current? So it's also going to be related to our power factor, right? So we know that our power factor is the cosine of the angle of our voltage applied. So this will be the angle of V phi A minus the angle of IA. We're just going to assume that this guy right here is 0, and just say everything is going to be in reference to that 0 degrees. So using this, theta IA is going to be negative the inverse cosine of negative IA. Excuse me, sorry. Let me write this, go a little bit further here. So this is going to look like the cosine of negative IA, like so. So theta IA should be it'll be like this. Let me sorry, I'm stumbling here, but let me explain what's going on with these signs because it's a little bit confusing. Okay. So from this relationship up here with our power factor, we can say that negative theta IA is going to be equal to the inverse cosine of our power factor. Because our power factor is leading, that's where this negative sign right here is coming from. If our power factor were lagging, that sign right there would need to be positive. Those two negative signs are going to wind up canceling each other out. And so we wind up just getting the cosine, or excuse me, the inverse cosine of 0.8. Which is 36.87 degrees. So the only reason that this angle is positive is because we're dealing with a lagging, or excuse me, a leading power factor. Putting things together, we then have IA is equal to 118.120 with an angle of 36.87 degrees amps RMS. And from here, we can calculate our induced voltage. So our induced voltage EA is 277 angle 0 degrees volts RMS minus our 118.120 angle 36.87 degrees amps RMS times 0.15 plus J2 ohms. And this comes out to be 451.139 with an angle of negative 26.263 degrees volts RMS. Finally now, so that should be a T, not an I. Our maximum developed torque of 3 times the magnitude of EA times the magnitude of V phi A divided by omega S XS is going to look like 3 times 451.139 volts RMS times 277 volts RMS divided by 188.495 radians per second times 2 ohms, and I get 994.447 Newton meters for our maximum developed torque. let's work one more problem, and then I think we're good with synchronous machines. So let's say that we have a three-phase 100 kVA rated (60 Hz) 480 delta 277Y volts RMS 6-pole synchronous machine has an armature reactance of RA is equal to 0.09 ohms and a synchronous reactance of excess is equal to 1.5 ohms per phase. The friction and windage losses are 2.46 kilowatts, and the core losses are 1.941 kilowatts. If the machine is used as a motor, operating at a power factor of 0.85 lagging, determine the motor's efficiency and output torque at full load. All right. So ultimately, we're looking for efficiency. So we know that efficiency, and I'll get it right this time, I hope, is the output power divided by the input power. And since we're working with a motor, our output power is going to be power delivered to our shaft divided by our electrical input power. So we need to figure out what P shaft is and what P electric is. We're also trying to find the torque at the output. So that is going to give us the relationship T shaft is equal to T shaft divided by omega S. So how do you think we're going to solve for any of these quantities? We can find omega S, absolutely. So omega S is going to be NS, and sorry, that should be an actual N, not an eta. NS times 2 pi over 60, just like in the last example problem, which once again is going to reduce down to 4 pi f over the number of poles. Skipping the intermediate conversions because we literally just used them in the last problem, right? So this is going to look like 4 pi times 60 over 6, which just comes out as effectively 40 pi. Or 125.664 radians per second. All right. So we've gotten one thing taken care of. Anything else we can possibly figure out? So I think you just said the current, which we definitely can find. So we know that our apparent power, which is something that was given to us, that's 100 megavolt amperes, excuse me, 100 kilovolt amperes. This is a three-phase machine, so that's going to be 3 times the line to neutral voltage times our current. I agree with that wholeheartedly. We could rearrange this relationship, and we would see that the magnitude of our current, IA, is going to be just our apparent power, S, divided by 3 times the magnitude of our voltage. So that's going to look like 100 kVA divided by 3 times 277 volts RMS. So 100,000 divided by 3 times 277. I get to be 120.337 amps RMS. We have a similar situation to last time. So without doing any derivation here, I can say that theta IA is going to be negative the inverse cosine of our power factor. And I'm keeping the negative sign this time because my power factor is lagging, right? So if we look back up here, at this relationship that we've developed, the inverse cosine of our power factor is equal to negative IA. Because our power factor is lagging, I don't add this extra negative sign in. So I wind up keeping the negative sign down here. And so this is going to look like negative the inverse cosine of 0.85 or negative 31.788 degrees. Putting those two things together, our current IAA comes out to be 120.337 with an angle of negative 31.788 degrees amps RMS. So let me ask you a question, Bailey. What are we going to use that current for, since you suggested that we find it? What? What apparent power was given to us? EA, okay. So we could definitely find EA. My question is, do we need it? Don't we need it to find? So let's think about this. So we need EA to find our developed torque. So that's the torque that's occurring because of the electromechanical energy conversion. But that's not the torque that we're looking for here. We're looking for the torque at the output of the system, which is just going to be the power at the output of the system divided by the speed at which our shaft is turning, omega s. Let's go back up to the power relationship, like the power flow diagram up here, and see if we can sort some things out, right? So the diagram up here on top is what we're using, okay? We're trying to find effectively the output mechanical power. We were told what our friction and windage losses were. So that's a known quantity. We didn't have any mention of stray losses, so we're just going to assume those to be zero because generally speaking, they would be mentioned. We were told what our core losses were. And I personally believe that we have enough information to find our stator copper losses. So realistically, if we can figure out what our electrical input power is, and then we subtract from that our stator copper losses, our core losses, and our friction and winding losses, we'll have our output mechanical power. Does that make sense? Okay, so the only two pieces of information that we're missing are our electrical input power and our stator copper losses. So what should our electrical input power look like? I think we have an equation for that. We actually have two different ways that we can do it, right? Our electrical input power is given to us right here. And we have all of those pieces of information. So I think that's a pretty safe bet. So we can say that P electric is 3 times V phi A magnitude times IA magnitude times the cosine of theta V phi A minus theta IA. But we're not actually going to really use that because this 3 times V phi A times IA is just our apparent power, which is known. And that cosine, theta VA minus theta IA, is just our power factor. So I think our electric power is 100 kVA times our power factor of 0.85 is 85 kilowatts. So now the only thing left for us to find is our copper losses. So the copper losses in our stator any thoughts on how we might calculate those? So copper losses are I squared R losses. And thanks to Bailey's suggestion, we found I. We were given R. So really we just take I squared times R and then multiply it by 3 because there are 3 phases. Right? So that's just going to look like 3 times the magnitude of IA, quantity squared, times RA. So that'll be 3 times 120.337 amps RMS squared times our resistance, which was 0.09 ohms, if my memory serves me correctly. And I believe this comes out to be 3.910 kilowatts. So our mechanical output power at the shaft is just our electrical input power minus our stator copper losses minus our core losses minus our friction and windage losses. And that relationship is coming from that power flow diagram that we talked about at the very beginning of class, right? So that's going to be 85 kilowatts minus 3.910 kilowatts. Our core losses were given to be 1.941 kilowatts. And our friction and windage losses were given to be 2.46 kilowatts. So that comes out looking like 76.689 kW. And now we have enough information to calculate both our motor's efficiency and the torque on the shaft. So our efficiency is simply the ratio P shaft to P electric, because this is working as a motor. So that's 76.689 kilowatts over 85 kilowatts. Comes out to be 90.222%. And our torque on our shaft is just P shaft divided by omega S. So that is 76.689 kilowatts divided by, let me scroll up here so I can find it, 125.664. Radians per second. And I get 610.271 Newton meters. My torque. So we could have taken the step that Bailey suggested to calculate effectively our developed power and possibly developed torque like we did in the previous example. But from the information that we were provided, I thought that an easier path was to just look back at our power flow diagrams. So there's nothing wrong with the way that you suggested, but it's not as efficient of a way to get there. Okay. All right, so that's enough out of me for today. We've finished with synchronous machines. So I'm gonna put a homework up for you guys that'll be due in a week. And then when we get back from the Mardi Gras break, we're gonna start on DC machines, which is the last topic in the course.